Okay, so I'm going to solve quiz 2. Okay, we had before. So quiz 2 was mainly CSTR in series, right? So similar concept we'll have in plug flow reactor as well. So okay, let's start one to one. Which of the compound contributes the conductivity? So as we know that we have sodium hydroxide and ethyl reaction of sodium hydroxide with ethyl acetate, right? Sodium hydroxide and ethyl acetate. So NaOH plus ethyl acetate gives you sodium acetate and ethanol, right? So as we said, NaOH will break into ions Na plus OH minus. Ethyl acetate is organic compound, it will not break into ion. So this doesn't have conductivity, this doesn't have conductivity. This one in the product will have. So sodium hydroxide and sodium acetate. So in this option we have only sodium hydroxide. If we have sodium acetate, yeah, it will also be having connectivity. Okay. Axial mixing is absent, which are the following. So mixing axial means along the axis. So along the axis in CSTR, CSTR is perfectly mixed. Okay. So in triple reactor we don't have axial mixing. Conversion depends on, of course, you have seen that by changing the flow rate, we can change the residence time. If we have more residence time, conversion is more. So this is true. At the same time, temperature, if we increase the temperature, rate constant will be higher, right? Rate constant is higher, it means conversion will be also higher. So this is true option. Now, um, feed flow rate to conversion. So this is what we did in PFR also in CSTR also. So when we decrease the flow rate, residence time increases, right? So if we decrease the flow rate, the residence time is volume of the reactor divided by volumetric flow rate, right? So if this decreases, the residence time will increase. So if your feed or reactant is going to spend more time in the reactor, conversion will be higher, right? Yeah, this you agree. But as we keep increasing tau, okay, conversion will increase, and then of course it cannot go more than 100%, right? So after some time, the amount of increase will be less and less and less. So after some time, it will be 90, 95, 96, and 98, 99. So not more than 100. So this relationship is not linear, right? Linear means like this, isn't it? A straight line. So this is not a straight line. So increases with increase in residence time, but not linear. Okay. So this is not linear with residence time. Okay. Now we come to this question. So as I told you that we gave you the data as we did in lab, right? As we did in lab. So we start with here. Concentration in the feed tank is 0.12. Okay, 0.12. So we had, if you remember, we had two feed tank where you put the feed NaOH and ethyl acetate. Concentration given here is 0.12, 0.12. And from here we take the feed to the reactor, right? So this is mixing somewhere, then it goes in plug flow reactor also, or in CSTR. So here is our Ca0 Cb0 after mixing in the reactor. Then it will react and give the new concentration will be Ca, right? So you need to make sure that you can find Ca0 and Cb0 after mixing. So it is like two just simplest mixing case. Okay, it is like a mixer. You have two stream coming to the mixer and it is going. One is leaving. So this is two, right? So the flow rate is Va, Vb, concentration in this case is 0.12. So if we say CAI, CBI, and then here is our Ca0, C CB0, CB0. So mole in equal to mole out. So A, this is volumetric flow rate, right? So volumetric flow rate means liter per minute, isn't it? Liter per minute, and this is mole per liter. If you multiply both CAI times VA, okay, that is mole per unit time. Mole in equal to mole out. So for from A balance, this is only stream we have A, and then Ca0 is the after mixing. Ca0, the feed flow rate becomes Va plus Vb. Okay, so Ca0 will be from here. This concentration is 0.12, and Va and Vb is equal. So in this case, Ca0 becomes 0.12 divided by 2. So this is the initial concentration, and same will be for B also, Cb0 also 0.06 molarity, right? Molar. So our initial conductivity and final conductivity will be based on this. Okay, will be based on this. Now what is our so lambda 0 and lambda infinity we have to find. Lambda 0 is basically, as we said before, it is initial conductivity before reaction starts. So Ca0 and Cb0. Cb0 is ethyl acetate. Ethyl acetate doesn't have any conductivity. So what we have, 0.06 molar NaOH. So just you have to find lambda 0, which will be lambda 0 is nothing but lambda of 0.06 molar NaOH. Okay, this one you can calculate using correlation given to you, concentration and temperature. Okay, you have a correlation, isn't it? Or for your easiness, this value is given. So 0.1 molar NaOH has conductivity 21. So 0.1 molar will have 21. So what will be 0.6? So 21 divided by 0.1 times 0.06, right? So this will be your initial conductivity. Now you need to find lambda infinity. Lambda infinity, again you have to understand that lambda infinity is conductivity of mixture when we assume that conversion is 100%. Okay, conversion is 100%. So what do we have now? You have NaOH plus ethyl acetate. Okay, A is NaOH, B is ethyl acetate, C is sodium acetate, D is ethanol. So we start with 0.06, 0.06. Okay, 0.06 molar A, 0.06 molar B. So after 100% conversion, we will not have A, we will not have B, we will have only C, and we will have D, right? 0.06, 0. So in this case now we have C and D. C is basically sodium acetate. Sodium acetate has conductivity. D is ethanol. It doesn't have any conductivity. So we need to find basically conductivity of lambda infinity becomes lambda of 0.06 molar sodium acetate. Okay. Correlation for sodium acetate conductivity is given to you. You can find, or you can find using this value given. We know that conductivity and concentration, they are proportional. Okay, so 0.1 molar ethyl acetate has conductivity 7.6 millisiemens. Okay, so 0.06 will have conductivity how much? So just using the proportional relation, 7.8 or 6, 7.8, 7.6. Okay, so 7.6 divided by 0.1 times 0.06. So that is lambda infinity. Okay. So now what we have? We have lambda 0, we have lambda infinity. We need to find concentration or conductivity, which is lambda infinity divided by lambda 0 minus lambda infinity. Okay. So this is lambda 1. Lambda 1 is conductivity in the tank 1 or reactor 1. So it is given to you. Tank 1 has 7.5. Okay. Tank 2 6.9. So if you put tank 1 7.5 and lambda 0, lambda infinity is known, 7.5 minus lambda infinity is known, lambda 0 is known, it will be around 12.6 minus lambda infinity, whatever value, you get Ca. Ca1, concentration in tank 1. So conversion in tank 1 is Ca naught minus Ca divided by Ca, right? So you can find the conversion 1. Similarly, conversion 2 using lambda connectivity 2, Ca0 minus Ca2 divided by Ca0. So this conversion of tank 1 and tank 2 is known. Okay, what else we have to find? Experimental rate constant. Compare experimental theoretical conversion for tank 2. Okay, experimental rate constant. Okay, so experimental rate constant, how we can find? Let me create word. Experimental. Okay, so for CSTR, you know this equation, right? Tau divided by Ca naught equals to XA minus RA, right? RA is KCA square, isn't it? KCA square. And CA is CA0, 1 minus XA, right? So this is a square. RA is KCA square and KCA is CA0, 1 minus XA square. So this is a square. So if you rearrange this equation, you will get K tau Ca naught equals to XA minus 1 minus XA square. So conversion, using conversion in tank 1, you can find K. Residence time is known, initial concentration is known. So that K is experimental rate constant because we used experimental conversion. XA1 we calculated using XA1 using connectivity of tank 1, isn't it? Ca naught and XA1. Okay, so experimental rate constant is known. Now we know the experimental conversion of tank A, experimental conversion of tank 2, 1 and tank 2. Now we need to compare experimental and theoretical conversion of tank 2 and tank 1. So for tank 2, this will be the equation. You have used it, okay? XA2 minus XA1 divided by K, 1 minute. So it will be, okay? So it will be XA2. From here you can see XA2 minus XA1 divided by 1 minus XA2 square equal to K tau, sorry, K, yeah, K tau C naught. So if conversion 1 is known, you can find conversion 2. Theoretical conversion 1, how we can find? So this is XA1 divided by 1 minus XA1 square equals to K tau C A naught. Okay, K literature is given to you. Okay, K value, literature value, theoretical value 0.1 something. Tau residence time, C A naught is given, right? 0.06. So you can find this value, okay, and using solver you can get XA1, XA1, XA1 theoretical, and then XA1 is known, you can get XA2 using this equation. So K same literature value, CA naught 0.06, residence time given, XA1 you know, XA2 only you don't know. So use solver, okay, to get XA2. So oh, hope this is clear. Now I saw solve full question this one, okay, and we had one more question which I can see in the quiz, but you can see this one 0.08 sodium hydroxide and 0.06 thiazide is pumped to CSTR in series at same feed flow rate. Okay, so this again concentration in the feed tank. Okay, before reactor. So Ca naught will be again half of this, right? 0.08 divided by 2, 0.06 divided by 2. So initial concentration is this molar, molar, Ca naught, Cb naught. Now what is required? Find the connectivity of the mixture assuming 100% conversion of limiting reactant. So limiting reactant is B. B is less, right? So A plus B giving you C plus D, right? A plus B given you C plus D. So now what we have? We have 0.04 molar, 0.03 molar, initially 0 and 0. So when connectivity is 100%, sorry, the conversion is 100% of limiting reactant, this will be 0, right? So 1 mole of B gives you 1 mole of C. So we will have 0.03 molar sodium acetate. C is sodium acetate. So D we don't care because it will not have any connectivity. Now we will have leftover NaOH. A. So 0.03 molar, this will also react. So we will have leftover 0.01 molar NaOH. So in this case, we need to find conductivity of 0.03 molar sodium acetate and 0.01 molar sodium hydroxide. Separately we will find, we know the concentration, we can plug into correlation, okay, given to you, and then we can add. So in this way we can find lambda infinity. This is basically asking about lambda infinity. Okay, so that's it. Hope it's clear.